Day 6, Finding Real Roots of Polynomial Equations. Today's objectives are to identify the multiplicity of roots and use the rational root theorem to solve equations. When an answer appears more than once, it is called a repeated solution. The number of times a solution repeats is the multiplicity of the root. When we look at a polynomial and we factor the polynomial completely, we can then state the multiplicity. So looking at 2x cubed minus 12x squared plus 18x equals 0, we can notice that there is a greatest common factor of 2x. So when we factor out a 2x, we are left with x squared minus 6x plus 9. After we rewrite the cubic in factored form, we can then factor further. X squared minus 6x plus 9 is a perfect square trinomial, and it factors to x minus 3 times x minus 3. We then need to set each of those factors equal to 0 and solve for x. So we get x is equal to 0, x is equal to positive 3, and x is equal to positive 3. If you notice, the positive 3 happens 2 times, and when you look at your graph where the 0 is at positive 3, your graph goes down to positive 3 and then bounces back up. So if we have a multiplicity that is even, or the number of times that a factor occurs is an even number, it's going to bounce. If the multiplicity or the factor occurs an odd number of times, then the graph is going to cross or cut through the graph. So you can see we have a 0 at x equals 0. That happens one time, and your red graph cuts through your x-axis. Find the zeros and sketch the graph of each polynomial function. Looking at example 3, we can see that f of x is equal to x to the 4th power minus 18x squared plus 18. I recognize that I can factor this function using the difference x squared minus 9 times x squared minus 9, because this is a perfect square trinomial. And then I then recognize that x squared minus 9 is the difference between two perfect squares. So to factor that further, I get x minus 3 times x plus 3 and x minus 3 times x plus 3. When I set each of these factors equal to 0 to solve for my roots, I notice that my roots are positive 3, negative 3, positive 3, and negative 3. So the multiplicity, or the times this happens, is 2. This happens 2. 2 is an even number, so it's going to bounce when it touches those zeros. So the first thing I'm going to do is plot my zeros on my graph. The next thing that I need to do is I need to look at my leading coefficient, and my leading coefficient is positive. I need to look at my degree. The degree of my polynomial is even. So if I have a positive even graph, it's going to open up to the left, up to the right. So I know that my graph has to bounce when it hits both of these zeros. So my graph will look something like that. Looking at example 4, f of x equals negative 2x to the 4th power plus 16x squared minus 32, I notice that I can factor a negative 2 out of this. When I factor out the negative 2, the remaining trinomial is x to the 4th minus 8x squared plus 16. I then can factor that further because it's a perfect square trinomial. And the two factors are x squared minus 4 times x squared minus 4. I then recognize that those are the difference between two perfect squares. So I have x minus 2 times x plus 2, x minus 2 times x plus 2. I want to set everything equal to 0. So negative 2 equals 0 doesn't make sense. Cross that guy out. X minus 2 equals 0. X plus 2 equals 0. X minus 2 equals 0. X plus 2 equals 0. So when I solve those, I get positive 2. One of my roots is negative 2, positive 2, negative 2. I have 4 zeros. Looking at my highest degree, I should have 4 zeros. So I'll plot a 0 at negative 2, plot another 0 at 2. To determine my end behavior, I need to look at my leading coefficient of the original function, and my leading coefficient is negative. I then want to look at my degree. My degree is even, so I know my graph should be opening down on both sides. So it's going to bounce, because my multiplicity happened an even number of times. And you just graphed your function. Not all polynomials are factorable, so we have what we call the rational root theorem to help find all possible rational roots. The rational root theorem has us list the factors of our constant term, which is the term at the end of your polynomial. And it also has us list the factors of our leading coefficient, which is whatever has the highest exponent. So in example 5, if they ask us to list all our possible roots, we know that our leading coefficient is our q, and our constant is our p. So we're going to put our p's over our q's. We need to account for all positive and negative possibilities. So in this case, the factors of 6 are 1, 2, 3, and 6. The factors of 3 are 1 and 3. And then we need to list all of those out. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Then I'm going to take them all, my numerators, and put them over my 3. Plus or minus 1/3 is a possibility. Plus or minus 2/3 is a possibility, and we don't want to list any repeats. So 3 over 3 is 1. We've already accounted for that. 6 over 3 is 2. We've already accounted for that as well. So our possible roots are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/3, and plus or minus 2/3. So to find all of the roots of the polynomial, the first thing that we want to do is we want to list our p's over our q's. So if we have our p's over our q's, the factors of 21 are 1, 3, 7, 21. The factors of 1 are just 1, so our possible roots are plus or minus 1, 3, 7, and 21. Make sure that plus or minus you take into account for everything. The next thing we want to use is synthetic division. So we make sure that all of our polynomials in standard form, we use the coefficients of those terms. If we're missing a term, we replace it with 0. And then we want to try one of our possible roots. If your numbers are small, you always want to try something small. Drop your first term, multiply, add, multiply, add, multiply, add. If you get a remainder of 0, remember from your the previous sections in this unit that means it is a root. So one of our roots is x is equal to 1. We know we need a total of 3 because that's our highest degree. So we can then write, using one exponent less than our original, our quadratic, and see if it's factorable. So I can factor x squared plus 4x minus 21 into x minus 3 and x plus 7. I then set those equal to 0, so my other remaining roots are x is equal to 3 and x is equal to negative 7. So you need to list those all out, circle them, and you just found the roots or the zeros of the polynomial. Our last example, we need to do the rational root theorem first, so we're going to put our p's over our q's. The factors of 12 go on top, so we have 1, 2, 3, 4, 6, and 12. Factors of 6 go on the bottom, so we have 1, 2, 3, and 6. So our possible roots, when we list them all out, are plus or minus 1, 2, 3, 4, 6, 12, 1/2, 3/2, 1/3, 2/3, 4/3, and 1/6. We then can use our synthetic division, 6, 1, negative 41, negative 44, negative 12. So depending upon how lucky you are at guessing, your first guess may not be right. I'm going to try negative 2, 6, multiply, negative 12, add, multiply, add, multiply, add, multiply, add. Yay, negative 2 worked, so one of my zeros is negative 2. Then we are left with a cubic because it's 1 less than our original, so we can use synthetic division again. The next number I'm going to try is positive 3. Bring down your first term, multiply, add, multiply, add, multiply, add. Again, our synthetic division works, so we're now left with a quadratic. We can then list our A, our B, and our C. The quadratic formula is the one thing that we know works every single time. So when we plug that in, x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So I get x is equal to negative 7 plus or minus the square root of 49 minus 48 over 12, which simplifies to x equals negative 7 plus or minus square root of 1 is just 1. So I have x equals negative 7 plus 1 over 12. And I have x could equal negative 7 minus 1 over 12. So I get negative 6 over 12, negative 8 over 12. So my other roots are negative 1/2 and negative 2/3. So in this case, all of our roots were real numbers. We have 4, so we list them out. Our roots are negative 2, 3, negative 1/2, and negative 2/3. So please remember that eventually we will be able to have complex roots, and if you are simplifying a radical, make sure your radical is always simplified to its fullest position, and you have to have all three numbers, one on the outside of the radical, one on the left of the plus or minus sign, and one in the denominator to simplify. So when you work out example 8, your roots would be 4, negative 5, and 2 plus or minus square root of 6.